I give you a rough overview. First of all, I start with presenting what I understand on a so-called socio-hydrological framework. We have developed such a framework in 2012, and we have used it in different case studies. And I will first go back to some kind of the physical environment. On the cryosphere changes, I will use one case study from Nanga Parbat, and here especially from Rupal Valley. We have just published 2 papers, and I worked on in the Nanga Parbat region starting in 1992. Then I will move to another case study in Ladakh, and there I will mostly focus on specific adaptation strategies that are used in this cold, arid environment of the Trans-Himalayan areas of Ladakh. And I will then go in the same area in Ladakh. I will focus on one GLOF event to bring another perspective that also cryosphere-related hazards are very important entry points to use the socio-hydrological framework before I come to the conclusion. My main framework, this socio-hydrological framework, is always based on these interaction that you can see on the left and on the right side, and feedback loops that are important between cryosphere changes and glacial-hydrological dimensions, changing glaciers, seasonal snow cover, permafrost, all the different components of the cryosphere, but also cryosphere-related hazards. As you can remember, the event in Kedarnath or the latest event in Chamoli in Uttarakhand gives you an impression that these cryosphere-related hazards sometimes have extreme magnitudes, and they cause a lot of victims and material loss. So this needs to be integrated, and I'm sure you have heard about these aspects in earlier UDAN lectures. But on the other hand, it also deals with the water availability, not only in the context of the continental scale water towers of the Himalayan region, but also on the local and regional scale, where villagers in different places of the Himalayan region produce their agriculture, and they are dependent on this water availability. In this context, the variability, annual and seasonal, are important, and always local particularities. And I will come back to these aspects in my case studies. We always have to see the potentials, limitations, and the risks that are coming with this changing water availability things. And the third dimension deals with the socioeconomic changes. What are the agricultural practices? How do they change over time? What is the role of, for example, irrigated agriculture for livelihood security? And what are external development interventions by the states or by non-governmental organization, and what does all these aspects have to do with the adaptation strategies? And when we talk about this, and now the next slide, we need to deal with these, with the case studies, and use different and glacial-hydrological methods together with socioeconomic methods like discussion, focus group discussions, and to also integrate the human dimension, the social dimension in this integrated framework. And in this map, you only see the 2 case study areas. One is Nanga Parbat for my first case study. That is the northwestern corner of the Himalayan region of the Himalayan arc. And my second case study, you're well aware of, that is located in the Trans-Himalayan region, in the cold, arid part of the Trans-Himalaya in Ladakh. And with this, I will start with the first case study with Nanga Parbat. It is one of the very prominent high mountain massives in the Himalaya, and we have developed a new glacier inventory, and I will give just a few aspects. It has been published a few weeks back in Science of the Total Environment, and I will focus on the glacier changes, but not only in the context to see in which dimension we face glacier changes, but what does it mean for the local population who have their subsistence agriculture based on meltwater related irrigation systems. In the Nanga Parbat area, we have a positive situation that we have a very detailed topographical map that was published in 1937. It was produced during German Himalayan expedition in 1934, and this provides a valuable baseline for the Nanga Parbat area. So we have there a long history of glaciological research that really helps to have a long range dimension to understand these changes. And as I said before, it's a prominent mountain that towers more than 7,000 meters above the Indus Valley, located to the north of the massif, and more than 4,500 meters to the Rupal Valley south of Nanga Parbat. And when I talk about the glacier changes, I will mostly focus in this presentation on the glaciers in Rupal Valley. Valley glaciers are all debris covered, as in many other regions of the Himalayan arc. And but what is important in this case, or very prominent, is the large role that avalanches play. As you can see in this photograph, the cones of the avalanche run-out zone in the south face of Nanga Parbat, on the Bijin Glacier in this case, that really plays a great role in the nourishment of the glacier. And that is also one case that is very special. It is a little bit like in the context of the Karakorum, that we face a lot of, we have very steep relief energy, and due to this fact, we have a huge number of avalanches that play an enormous role in this glacier situation. And just to give you a short overview from our inventory, we have only 7 glaciers that with a huge area with 207 kilometers, square kilometers, and the majority of glaciers are very small, as you can see here in this graph. And most of course, the valley glaciers are debris covered, and the clean ice glaciers are located in the upper regions. And the second point is the altitudinal distribution of clean ice glaciers and debris covered glaciers. This is not an unusual pattern that we have at altitudes below, let's say, 4,000 or 4,500 meters, more and more debris covered glacier, and the higher altitudes always covered with clean ice glaciers, as you can also see on the satellite imagery. And now I will come in detail to the south face of Nanga Parbat, this Rupal face with 4,500 meters of relief energy. I told you there are a lot of avalanches, and the valley glaciers like you can also see one of them here, mostly debris covered. And in this context, I would like to ask for the next slide. This is a map that shows the Rupal Glacier in the lower part here between areas like Rachmanpur, Churit, Tarishing, and the village Rupal. We have irrigated agriculture, and in the upper part, of course, we only have the glaciers. And you can assume that as 75% of the total runoff depends on cryospheric meltwater, and the villages are located there, that in one or the other way, the glacial meltwater is very important for this irrigated agriculture in these arid valley zones of the northwestern Himalaya. We also have a very old material dating back to an early colonial explorer, Adolf Schlagenwald. He was one of 3 brothers who went there for 3 years. And Adolf Schlagenwald also visited the Nanga Parbat area, and he prepared the first draft map, a sketch map that shows the location of the glaciers. I will come back to one of them a little bit later. And he also produced some of these paintings that show the glacier situation at that year in 1856. And we use these parts of the Schlagenwald sketch map to confront it with the Finsterwalder map from 1934 that was published in 1937, and some remote sensing analysis. And so we were able to detect the changes or in length for this exam. For this case, it was 23.4 kilometers in 1934, and later on it was reduced. This glacier, this Chungfa glacier, touches down to an altitude of 2,910. That is relatively low. If we compare it later on, we will see it is completely different in the case of Ladakh. And we have a total retreat when we go back to 1856 to 2020. It's a total retreat of 1 kilometer. And now there's a series of repeat photography. The first one is taken by Richard Finsterwalder in 1934 during the production of this topographical map. And you see the outlet, the mouth of the Chungfa Glacier, and the next shows the same glacier from the same location in 1956, and the next shows the same glacier. You can hardly see it around the corner in the year 2010. By the way, in 2010, that was the year when we also had this massive cloudburst event in Leh and other parts of Ladakh, where we faced a lot of destruction, and at the same time, or 1 or 2 days later, it also occurred here in the Nanga Parbat region, and you can see this road was destroyed and the bridge was completely destroyed in this context. But what is important here for our context is we have a retreat in this glacier, and the next we also can see we have changes in the surface, in the volume of the glacier. And here we also used some historical photographs from 1934, from 1958, from 1987, and my replicate was from 2010. And in this context, you see that there is a thinning, a general thinning from especially between 1934 and the lower left one here is 1987. But you can also see that on the other hand, there's an increase of volume here, and the mechanism behind that is that 2 of these glaciers on the south face of Nanga Parbat also have this surge kind of behavior in certain periods, that we have some surge events. Here in this case, it was 2008, 2009 when this surge happened, and we were able to identify another one in 2015. So there's also a problem with this changing elevation of the glacier surface, and I will come back to this problem a little bit later. The last glacier I want to show you here is the Rupal Glacier in the upper valley head. And I start again with the Schlagenwald sketch map on the right side. You can see Adolf Schlagenwald tried to differentiate the clean ice from the debris-covered glacier in 1856. And of course, the illustration is much clearer in the 1934 map of Finsterwalder, but you can also see the same thing in high-resolution satellite imagery. In this case, the quite long, relatively huge area glacier of Rupal, the main Rupal glacier, also decreased in area and in length, and we have a total retreat in length 1.1 kilometer over the whole period between 1856 and 2020. Again, a photograph that shows the Rupal Glacier. Here you have relatively less avalanche impact than from the south face of Nanga Parbat, but of course you also have a few additional avalanche inputs here on this glacier. The 1934 photograph unfortunately had a fresh snow cover, and my replicate, the next one, the replicate was taken in August 2010, but you can see there's also, like in the first case, a massive downwasting. In this case, we calculated some 70 meters of downwasting between 1934 and 2010. And I want to come back to the overall situation of glacial length changes in the Rupal Valley, south of Nanga Parbat. And the main aspect is, it's not surprising that the glacier in retreat in length, all of them, only a few situations where we have, as I told you before, the surge type behavior of Chungfa Glacier, and also in other glaciers we have some signals of small surge events, like they are described for the Karakoram range by a number of authors, starting with Ken Hewitt and later on by Rakesh Bambri and others. The Karakoram anomaly is relatively well discussed, but it was not clear, it was never described that we also have these surge type glaciers in the Nanga Parbat region in the northwestern Himalaya. And what is more important for our socio-hydrological interaction where we talk about meltwater dependent irrigation system are the surface changes. And in most cases, as you can see from the red colors, that was the first glacier, the Chungfa Glacier I showed you, and the second one was the main Rupal Glacier. Here everything is only in red, and it has a very negative surface change, as I told you before. But in some cases, we also have, due to this surge situation, in small parts, a positive situation here between 1934 and 2000. And the next, and after 2000, we also analyzed these situation And what is important now is when we see the profiles of these glaciers at various altitudes. For example, here in Chungfa, you can clearly detect the lateral moraines on the side, and these lateral moraines produce some kind of problem that you see in the next slide. And this shows the irrigated agriculture that was digitized here for all villages, Tarishing and Rupal and others between in this area. And the interesting thing is that when we checked the 1934 map, it was possible to irrigate this fields of the village Tarishing directly with meltwater from the Chungfa Glacier. And this is now no longer possible due to down wasting of the glacier surface. And it means that the villagers have to organize their workforce and find other water sources. There are still enough in this area, but it means to build new irrigation channels. It means to find new meltwater entries to secure irrigation in the context of this subsistence-based agriculture in these valleys. I come now to my second example I will continue on these adaptation strategies in Mangapa, but I've just make it very short with these new irrigation channels that have to be found due to the situation that the cryosphere to cope with cryosphere changes. In this context of Ladakh, it is very clear. It is also located in the Upper Indus Basin. We have a clear system of meltwater discharge that is distributed along different channels and then distributed to the fields. And in this slide on the right-hand side, you see the glaciers in Ladakh are located at high altitudes in this arid part of the Trans-Himalaya, and they are completely disaggregated from the cultivated areas that you can see here in these different hues of red. The interesting thing in the context of Ladakh is that the glaciers are located at high altitudes, and none of them in the central part of Ladakh is lower than the mouth of the glacier is lower than 5,200 meters, and almost all of them are very small, towards the east, towards the lakes like Pangong Lake or Tsomoriri, the minimum altitude of the glaciers even increases to altitudes of higher than 5,800 meters. This is a particular situation in Ladakh, and this is again my entry slide, and this really shows the direct combination of meltwater dependent irrigation systems. In this context, it's the one village of Hanka in the Maka Valley of Ladakh, and it directly depends from meltwater from these glaciers and also from seasonal snow cover and permafrost. The agriculture is always subsistence-based, and it's crucial for rural livelihoods and, in this context, for food security. And over all of Ladakh, we have a very limited introduction of cash crops. It's mostly barley and a few other additional crops. The problem with the high location of the glacier is that meltwater sets in at a relatively late point. Only from mid-June onwards, we can be sure that the meltwater discharge from the glaciers is high enough to meet the demands of the for agricultural production. So in this context, it is clear that between the sowing period and the onset of ample meltwater discharge, we have a recurrent water deficit that occurs every year. And to bridge this critical phase, the people in Ladakh have developed a certain adaptation strategies that I will focus on. They were mostly called artificial glaciers, but I will tell you a little bit about this context and why I prefer to use the term ice reservoir. Yeah, we have different types of these ice reservoir types. They are always located at altitudes below the natural glaciers, and they are always located above the irrigated villages or the tree plantations. And we have one type, a typical cascade type. I would show you photographs from these areas. Or we have a diversion type where the main meltwater stream is diverted to often shady places where we also have a cascade of small walls. And the third type is a basin type. This is a classical type that has been established in Ladakh over many centuries. It's a traditional way of irrigation. These types of basins also exist in the villages. Then they are called zings, and but they are also used to catch water as a water harvesting method in order when ice is accumulated. And the last type is this innovation of the so-called ice stupa that was introduced by Sonam Wangchuk, a Ladakhi engineer who uses a more sophisticated system with a sprinkler, and you need to have a hydraulic head so that water is for the whole time running. And now these ice stupas exist in various villages, as you can see from my co-author, from this photograph from my co-author, Susanne Schmidt, from the last stay in Ladakh we had before COVID-19 made different things quite difficult and impossible. You all know about this. And it is quite interesting that these types of ice reservoirs, here you can see a successful ice reservoir in Igu located at 4,400 meters. This is taken during the summertime. These ice reservoirs, obviously, they are only seasonal ice storage structures. But the different types I already introduced you, the cascades and the basins and the ice stupas are located in different parts of central Ladakh, as this map shows you. The functioning of these ice reservoirs is relatively easy in most cases. These traditional ice reservoirs, we have a series of small walls, and they are used to reduce the flow velocity, and with temperatures well below the freezing point of water, we have a more robust freezing process, and when water then flows on the ice surface, it refreezes again. And with this superimposed icing patterns, in the end, we have a compact ice body. In many cases, it is then even higher than the walls, and what we need for this is obviously a high frequency of restore cycles. And one of the most important questions is, are these structures convincing solutions to cope with the adverse effects of climate change, or are they only useful to bridge this typical critical phase during early spring and the phase between the onset of the vegetation period and the time when enough meltwater is available from the glaciers. This is one typical example here in this context of one of these ice reservoirs. Here you see in the central part that one of these walls is already overflown with ice. So in this context, we have an ice accumulation between 2.5 and 3 meters thick. So this is a very successful water harvesting possibility to increase meltwater availability for the villages. And here, this is also a very long structure in one of the upper parts of Ladakh in a village called Pukse, where we have a structure that is more than 800 meters in length, and we have 20 to 50 meters long walls that allow this long structure to be built. I took this photograph in February 2014, and I revisited the area to have to check the situation without ice accumulation, and this is the result. And this is another type of ice reservoir. This is the so-called diversion type. In the photograph in the upper part, you see you can detect the diversion channel, but the cascade system is similar. These systems are a bit smaller, and you can see how high the walls are. In this context, they are 20 meters wide, and the whole structure is roughly 200 meters long. And when these structures are filled, then it is in this situation. And this is the person you can see standing on one of these walls. He is the Chutpon, the water warden of the village, who has certain responsibilities to ensure that a regular flow is guaranteed, so that we have, in the end, a good formation of ice over the time between. The ice formation starts in November and it ends in April. And we use the structure from motion technology or method to have a model of these structures, and this was taken in 2015. That was a year when we had not such a very successful ice formation, but only here along the irrigation, the diversion channel, we had some ice, and in the upper parts, yes, then we tried to calculate the volume of these ice reservoir. But in this year, when we took the measurements, it was, as I said before, not a very successful year. So the numbers you can see here about the volume that are the minimum volume that are required in this year. In other years, for example, in the year before, in 2014, it was much more, but in this year we did not use the structure from motion to calculate the volume. Then we checked all the 14 different ice reservoirs we checked using remote sensing data from the 1990s to 2015 and differentiated to the different types: cascade, diversion, basin, and the ice stupor. The ice stupor at that time, it was only very new, so we cannot really say from when we calculated, when we did this research in 2000 until 2000, end of 2015. Now it's we have much more of these ice stupors. But what we can see is not in every year all the structures were really successful ice filled. Sometimes we had no snow and ice at all, and in other cases it was under construction, and there were maintenance and repairs, so that we cannot say that in every year all the structures were successful, but at least some structures, mostly the cascade types, were really very successful, and one of these basin types also was successful in ice storage, and in this way this water harvesting strategy that was really a successful thing. But coming back to the question whether we can use these ice reservoirs that are commonly termed as artificial glaciers, although it is only a seasonal ice formation, although it has no accumulation and no ablation zone, and it is only structure that a man-made structure that is used for seasonal water harvesting in a very innovative way. And these innovative structures were based on traditional environmental knowledge of people in Ladakh, and they were assisted by one of these larger non-governmental organizations that who are active in Ladakh for the last 15, 20 years. And one engineer really organized to assist different villages in building these structures. And as you can see, some of them are very successful. But on the other hand, it is not really clear that, that these structures can serve as adequate solutions to cope with climate change. This needs to be organized, this needs to be investigated with further studies. It is also important, I told you about this Chutpon, the water warden. He has the responsibility, for example, to open the entry points for this cascading system. And it's all too often when the temperatures are very low at these altitudes of 3,800, 4,200 meters during winter, well below 0 degrees. Sometimes it must be -20 or even lower, at least at night. And in these situations, it's always the problem that the entry points are frozen and not enough water comes to produce more ice. And the problem in this context is that it is necessary to integrate a huge amount of human workforce to maintain these structures over the winter time. I will come to my last point, and this will deal with cryosphere-related hazards, and I will focus on one particular case study of a GLOF that hit Gya, a village in southern Ladakh, and this is the place of Gya when we visited it in 2014. roughly 3 weeks after this glove. And at that time, it was a strange situation. The people told us that they faced a high flood that destroyed a few houses, although there was no rain. And it's just to show you here in the middle of the map. I'm sure I cannot show you it with my pointer right now, is the location of Gya to the east of the Kangyatse Massif in central Ladakh. And first of all, we have organized an inventory. We have mapped all the glacial lakes, and we have classified them, the typical lake types, especially proglacial lakes that are mostly very relevant. And just 4 days ago, there was another glacial lake outburst flood in Ladakh, in the main Indus Valley, coming from Rumbuk, from the Stok Range, and it also caused a certain, but it was not a very massive flood that destroyed many things. One bridge was destroyed. And then we checked about the different lake areas, and we visited different of these glacial lakes in Ladakh and here it was important to see what are the dynamics of these different glacial lakes. Some of them increased relatively large. And when we started to work on glacial lake outburst floods in Ladakh, it was not really a very important topic. We have huge glacial lakes in other parts of the Indian Himalayas, in Sikkim, for example, or also in Uttarakhand, and but not so much in these arid parts, because all the glaciers, as I told you before, are located at very high altitudes, and the glaciers are relatively small. And likewise, the glacial lakes, the meltwater lakes, are relatively small. And I will show you now one particular case, this case of Gya. It is located to the east of the Kangyatse range, that is here in the white rectangle. We have worked on these glacier changes on Kangyatse a few years back, and we estimated all the glacier decrease and the mean front retreat in this massif. And yeah, because of that, we also have a number of glacial lakes in this massif, and one of them was the one that caused this problem. Next, please. And it was this one, located at an altitude of 5,400 meters. And here you can see in the lake is almost always has a frozen surface, and there's also some calving thing. And you can imagine that when the glacier here in the background collapsed, then there will be waves, and the terminal moraine will destroy it, or avalanches from these sites. And there are different possibilities of a glacial lake outburst flood. I took this photograph a few weeks in October after the August event of the glacial lake outburst flood. Next, we checked the structure of the village of Gya, and we started to use an old cadastral map, a colonial map from 1908. This is the main channel, and this is the part in the, you can see in red the location of the village and the cultivated fields in green. And Gya was an important place along the historical trading route between Kulu and Leh. and it was a halting place. It has a rest house and grazing grounds for roughly 40 households, according to the Gazetteer of Kashmir and Ladakh from 1890. It's located at an altitude of 4,100 meters. And then we used satellite imagery to map the land use pattern in 2013. In this case, we used the spot image, and now we can see all the different houses and the different fields. And now it is the highway between Manali and Leh. It has some 700 inhabitants now, at least according to the 2011 data. And it is prominent for the irrigation of barley as almost all other villages in Ladakh. The glaciated area in this part, in the upper part of this channel, is like in other parts, also above 5,400 meters. And when we saw all these destructions here, a massive concrete bridge here, a few houses, and the loss of some of these cultivated fields due to this massive flood, it was a situation that, fortunately, no loss of life or injuries happened in this situation, but the fields of 14 families were affected, and a few houses were partly or completely damaged. And the most important thing was one hospital was really damaged in the lower part of the village. And this is the situation. On the right-hand side, you see the village of Giyar, and then the whole channel. And in the upper part, on the left side, you see the glacial lake. This is before the flood. And this is then on 11th August after the flood. And then we combined these two satellite images, and this is then the next, and we subtracted one from the other, and there we can see what has the change in the land cover that occurred after this flood. A number of photographs from the channel between 5,310 meters. This is near the lake, near the terminal moraine of the lake, and in lower parts and on the lower right hand, you see the part of the channel near the village of Giyar when it enters the village. So you see a lot of sediments, a lot of destruction along the way. And our question was, what caused these floods? Was it a calving glacier? Was it coming from one avalanche from the side? Well, no avalanche, it was in August. But nevertheless, our first guess was it came from a calving glacier or from some material, a landslide that from thawing permafrost or something like that in this context. But then we checked it, the massive moraine, this is 500 meter wide, and the problem of this moraine is that the moraine includes a huge mass of buried ice, and the lake is almost always ice covered with very few exceptions. And when we use the old American espionage satellite data, Corona, from the late 1960s and 1970s, there we could detect the lake it was only very small, and it increased in size 3 times until 2014. And this situation, this is a rapid eye photograph from shortly before the outbreak, the outburst. And then we had good luck to get a Pleiades image from the day the outbreak happened, the outburst happened, and you can see all of a sudden we have an open water in this lake and a small lake in the middle, but obviously there was no overflow of the moraine, but the water came out at it penetrated through the moraine. It was a piping process, a tunneling process, and it reappeared at the surface, at the lower part of the moraine. And you can see in the valley part, huge parts in this situation inundated by water from this lake. And immediately, a few days after the outbreak, we have the same lake area. It increased by a few parts of a square kilometer to 0.11 on the day of the outbreak, but then it get the same size as before. And yeah, it was no destruction of the terminal moraine was possible to report. Next, and we calculated a maximum of 5 meters of water level that was possible, that it was released in this event, and it sums up to some 83,000 cubic meter of water that was released during this event. And when we checked all the satellite images starting from 1969 with this corona imagery until 2014, in almost all cases, we found that the lake was ice covered, and that's why it was not included in earlier inventories. And obviously it was a big problem. Only in few individual satellite images we could really detect open water. Next, please. And it was obvious that in this event we had a clear fluctuation of the lake level in this year 2014. The arrow in this context must be a little bit to the right side to where we have the different number, the different altitudes, the lake areas. And when we reconstructed all the different satellite imagery, there were other years in which we could find that there were very rapid changes in lake area of this particular lake. And from our interviews with the villagers, we heard that around 30 years ago, they were not able to produce a more precise data. They also experienced a small flood which damaged some cultivated fields, and that was not correlated with any kind of torrential rainfall event. But in this situation in 2014, we had a very long period of high radiation and very good weather 2 or 3 weeks in a row, so that we cannot discuss anything about a rainfall event. It was definitely a GLOF. And then we revisited the Gyar Lake in 2019, and it was interesting. From the ice on the shores of the lake, you can see that there were again some fluctuations of the lake level that have to be taken into consideration here for this lake. So we can assume that we have a certain release through piping, and it's But this was obviously not, we also discussed it with the villagers, and this was obviously not a very significant GLOF event in 2018, 2019. And yeah, the moraine, the terminal moraine has this situation with the outlet and the upper part of the channel, where we first thought the water was released through this part. But it was definitely not the case, because in the terminal moraine we found some plants here, in this case this typical cushion plant Thylacosphaermum caespitosum, that is very typical for upper parts of Ladakh, and it was completely intact and not destroyed at all, so there was no overflow on this moraine. But obviously, we saw a lot of buried ice in this moraine, so that it is very clear that we have seen, or the villagers have experienced a tunneling of this morainic body. What was interesting, in 2017, 2018, they again built some small bridges in the same situation, and that was kind of problematic. Here's again part of the main highway between Manali and Leh. This highway was fortunately not destroyed, only a very minor problem with the main accessibility access for Ladakh. So, but the problem is with this construction, this reconstruction of bridges is problematic in this context. So I have a few lessons from the Gyar case. Of course, there's an increasing probability of cryosphere-related hazards, and this definitely, not only in the case of Gyar, but everywhere, it requires local disaster awareness and preparedness campaigns, and this has to be combined with efficient and reliable early warning systems. And in places like in Sikkim or also in Uttarakhand, things are on their way, but in the case of Ladakh, it is still in the very beginning. Technological monitoring solutions are important, but they should always be combined with site-specific land use planning and adequate climate change adaptation strategies. Of course, in many Himalayan areas, we have an urbanization process with new settlement parts in sensitive regions, in sensitive parts, also new infrastructure development. When you see, for example, the Chamoli event in Uttarakhand, the two hydropower installations in the upper part, this definitely always increases potential loss and damage of floods. And yeah, as the case of Gyar also showed, although there were no human victims, these small GLOFs can also be potentially harmful for the local population, because they all too often also destroy the irrigation infrastructure, the intakes for water abstraction or the water channels, and they also destroy the wetlands in the upper parts, and these wetlands are important for water storage during to bridge dry periods. What is always important is also that the stakeholders, the villagers and NGOs in this context is a precondition, a crucial precondition for developing successful measurements of interventions. And it's always important to integrate local environmental knowledge and experience. And for this, I think integrated socio-hydrological studies are quite important. Next, so I come to my last points to conclude the three different case studies, Nanga Parbat, Ladakh. And I think sociohydrology is quite a useful integrated framework to analyze the interactions between cryosphere dynamics and local irrigation networks, also including the site-specific particularities of different regions in order to understand also the risks from cryosphere-related hazards. And as I said before, even small glacier changes may have serious consequences for local irrigation practices. You can remember the case of the thinning of the glaciers and the problems with the intakes for the irrigation channels. And of course, as there are many site-specific particularities along the Himalayan arc, the local adaptation strategies always vary across the region, and they may include technical solutions like new irrigation channels, or in the case of Ladakh, ice reservoirs, or installation of water pipes. But the dynamics of land use, they always need to be contextualized with socioeconomic pathways, because in this context, we also have to ask questions. In this talk, I did not focus too much on it, on the availability of agrarian workforce for the maintenance of the irrigation network, and for the changes of accessibility of former remote mountain regions and the supplies of external food supplies. In the case of Ladakh, it is organized through a state organized supply system. And that was my first slide. And I would like to give my last comments on these socio-hydrological constellations. We have different components: the local land use practices, water resources, also the hazards and the external influences, and a number of crucial aspects need to be taken into consideration to find the entries to have a more integrated framework that tries to combine the natural dynamics, the glacial-hydrological dynamics, with the socio-economic response patterns and adaptation strategies to find a better solution. And it's always an analysis of the persistence of change. And the very last photograph shows you again the situation. I think it is roughly 10 years after I took the first photograph from this location. And it's only to show you as a symbolic thing that there's a high grade of persistence in these land use patterns, although we have a lot of dynamics in the natural environment, and we have a lot of socioeconomic processes and changes in this context. And with this, I would really like to thank you for your attention.